153, which is a special version of differentiation called implicit differentiation. And it's designed to do one job, and that is to find derivative of guys that look like these. These are called implicit expressions, sometimes called implicit curves. And what makes them different from a normal function is that they're not written as y equals a function of x. You see the x's and y's are all jumbled up. So it's pretty obvious when you see an implicit expression, it's all jumbled up. If somebody said to you y equals x cubed plus 2x plus x sine x, then that would just be a normal function, and we know how to do that. So these are all examples of curves called implicit expressions. I've got them set up in Desmos so you can see what they look like. And hopefully you're looking at Desmos right now. Right, so x squared plus y squared equals 25 actually makes a circle radius 5. And if you change that number to something else like 36 or 4, you just make different size circles. Let's make that one go away. Now this one is full of x squareds and y cubes and xy's. So what you're looking at here are all the points in 2D space where if you take the x coordinate, square it, and then double it, and then you add 2 times the x coordinate times the y, and then you subtract the y coordinate cubed, it's always equal to 1. So that should be quite interesting to see. And if I zoom in on it, do you see it's got a funny little bump? It's not a function. If you remember in 141, if you do a vertical line, shouldn't it only cut the curve once? And here it definitely cuts it more than once. So that's why I'm not calling them implicit functions, and I'm calling them implicit expressions. Now, if you take this as an example, if I take the point where my mouse pointer is here, hope you can see my mouse pointer, it's got a tangent line. In fact, at any point in that curve, couldn't you draw a tangent line? And if you can draw a tangent line, it means there's a derivative there, right? So you should be able to differentiate it, because a derivative is just the slope of that tangent line. Right, make that one go away. Now here's one that will break the computer. See, it looks okay until you move over here. So you can imagine that implicit expressions can really generate some very weird shapes. And here's one that looks like a fraction. And go. And it's actually not that bad. Although, it looks like it's got a little hole. Can you see it, a little break? And that must happen when that part is 0. So if you're looking for that, there's probably some places where that happens, and that's what is caused by that. So are you comfortable that these implicit expressions make curves, and curves can have tangents? And that means their derivative does exist. So our job is to find what these derivatives are. And as you can expect, because there are so many different versions, and there's a lot more than this, the process of finding them is not an equation. There is no implicit differentiation rule, right, where you could just, you know, put an F dash here and a G there and you get the answer. It's totally a process. So here is the process. It's very cryptic and very short. But if you want to find the derivative of an implicit expression, we'll call the derivative typically dy by dx. If you want to find dy by dx of one of these guys here, anything like that, the 2 steps: differentiate each term with respect to x on both sides of the expression. And the second step is basically find dy by dx by solving an equation. So before we get into that process, here's a little side process. Here is what you get when you differentiate little pieces of that expression. Let me cover this up so we only look at one at a time. If you differentiate x cubed, you still get the power rule, you still get 3x squared. On the other hand, if you differentiate 4y cubed, you do the power rule, multiply by the power, reduce it by 1, you get 12y squared. You also get, anytime you differentiate a thing that's got y in it, as we have here, not only do you get the normal answer, which would be 12y squared, you always get a dy by dx. It's caused by the chain rule. Because you think of y as a function of x, that's like your inside function is actually just y. So it's derivative times dy by dx. If you do e to the 5x, your little chain rule, you get that. If you do e to the 5y, do you notice you get the exact same expression? Just remember to finish with the dy by dx. That's the trick. Whenever you're differentiating an expression that contains only y's, do the same thing you would do if it was x's, but remember to finish with a dy by dx at the end of it all. And there's a sign, and there's a sign y. So like many things in calculus, the best way to deal with them is to do as many examples as you can. So here is our first implicit expression. 4x cubed plus 2y cubed equals 10. First step, differentiate everything with respect to x. Now, if you differentiate 4x cubed, it's a power rule. Multiply by the power, reduce it by 1. If you differentiate 2y cubed, right, it's a power rule. Multiply by the power, reduce the power by 1. And what do you finish with when you differentiate 2y cubed? The answer is not just 6y squared. What do you finish with? What else?
Y by dx.
That's it. Now, as long as you remember that, you pretty much know how to do implicit differentiation. Of course, occasionally you get caught out with things. What's the derivative of 10?
0.
0. So that's step 1 done. Differentiate all the terms. Okay. Now, the second step is solve for dy by dx. And I want you to use a trick that we use a lot in solving equations that I call, as long as you do it to both sides, it's okay rule. So here goes. I am going to subtract 6x squared from both sides. What do you think I'm now going to do to both sides to find dy by dx? What am I going to do to both sides?
Divide by 6y squared.
Great. Okay, it's a nice simple one, but it basically shows you all the bits that you need. I can't think I've ever done a question where I don't at the end either say it or it's kind of obvious what's going on. Would you agree that style points should take over? In other words, if you can, factor everything, make it look like the original, simplify. There's not an awful lot to be done here, but I can do a little bit. Are you comfortable about dividing top and bottom by 6 and just getting 2 on the top and a y squared on the bottom? And you are finished. That is your first example of finding the derivative of an implicit expression. So if you wanted to know what the slope of the tangent line, of one of those weird curves, whatever it ends up being, don't you need to just plug the x and y coordinate in here, and that's your slope? So it does allow you to get the slope of a tangent line. Now we're moving quite rapidly. Each one gets a little bit different and a little bit more difficult. Now, each one of these pieces is going to get differentiated with respect to x. If you differentiate x squared, you'll get 2x. And if you differentiate x, you get 1. This expression in the middle, 4x squared y cubed, it's essentially a product. It's two things multiplied. That guy's f and that guy's g. That means that if I want to differentiate this, I'm going to have to do the product rule. Does that seem reasonable? If you want to find the derivative of 4x squared times y cubed, since it's a product, aren't you going to have to use a product rule? So this guy's still 2x. If you differentiate f, you get 8x squared. Leave the second function alone, plus f left alone. And now you need to just differentiate y cubed. And differentiating y cubed, you get 3y squared times dy by dx. And the whole thing's equal to 1. There's step 1 finished.
Wait,
think
is
you
the
accidentally
derivative
left the
of
square.
4x squared 8x or 8
Yeah.
Yes.
squared?
Oh God, I've put an x squared. Well got. Yeah, 8x. Apart from the fact that I wrote that squared down. Are you comfortable with this guy, product rule, and 1? Right, this guy, the product rule, and 1. Okay, at this point, we now go into solving for dy by dx. Okay, tell me some things I can do to both sides to get closer to finding dy by dx.
You could add minus 1, then add 4x squared times 3y times dx. Then divide by 4x squared times 3y squared.
Okay, I think you said all probably in one go, which is fine. But for the rest of us, I think we'll slow it down a little bit. So I'll take away those two terms from both sides. And while I'm at it, I might as well multiply these together. Okay, so that's what I think I heard, right? And then you divide everybody by this fella. So you notice it was subtract things from both sides first, and then at the end, do a division. And that's us finished. So essentially 2 steps. Step 1, which is this bit here, is differentiate everything with respect to x. And then step 2 was solve for dy by dx, and you do that by adding things to both sides, subtracting things from both sides, and dividing both sides by the same thing. Each time I do one of these, as we go through this list, something is going to be a little bit different. Okay. Well, we have x e to the y on the left-hand side, and we have x take away y on the right-hand side. This is an implicit expression. And so we're going to differentiate each of the pieces in no particular order. If you differentiate x, you get 1. If you differentiate negative y, you get negative 1 times, remember, anytime you differentiate a y, do what you would normally do as if it was an x, but finish with a times dy by dx. So when you differentiate negative y, you get negative 1 dy by dx. So that seems reasonable. Now over here, I have 2 things multiplied. So we're going to do another product rule. So it's going to be f dash g plus f of g dashed. If you differentiate x, you get 1. You leave g alone, you get that. You leave f alone, you get x. Okay, anybody want a shot at differentiating e to the y? What would that get you?
Wouldn't it just become e to the y times dy over dx?
It would indeed. And this thing here is 1 take away dy by dx. You agree you don't need to write 1 dy by dx. Now, what makes this a little bit different from the other ones isn't this the first time that we've got two different places with dy by dx in it? You see there's a piece here and there's a piece here. And we're still going to use that as long as you do it to both sides rule to eventually get a single dy by dx equals some horrible fraction over on the other side. So the way my brain works is I says, okay, I got a dy by dx here and I got a dy by dx here. I need them to get together. So I'm going to add a dy by dx to both sides. Right, so I'm going to add 1 dy by dx to both sides. And that leaves me with that guy. And now I don't like that guy there. I want him to go away. Right? Well, if I want him to go away, I will subtract e to the y from both sides. Of course, you could have done that in one step rather than two. Are you okay so far? Right. So if you have two places with dy by dx, your first goal is to get the terms that have dy by dx on the left equals the things that don't have dy by dx on the right. Anyone take any idea what the next step is? Because it's actually pretty typical. You'll do this quite a few times.
Factor out the dy by dx.
That's exactly what we do. You nailed it. And that leaves me with what? X e to the y plus 1. Well, this is it. What do I do to both sides then to get dy by dx?
Divide by e the by x e to the y plus 1.
Yeah, divide by that ugly guy. I tend to just call them ugly guys. I should look at that to see if there's any factoring, cancelling, combining. It's pretty obvious to me that I can't do anything, which means I'm finished. There's your answer. Now that's only 3 examples. Do you see that there's a lot of variation in what they look like? Even if the process hasn't changed, I'm still basically doing my step 1, which differentiate everything with respect to x. And if there's any terms that have a y, to remember when you differentiate them to finish with a dy by dx. 4 is a trick. Sine of x plus cosine of y is 9x, take away 4y. Now, if you want to differentiate each piece, differentiate a sine x, you will get a cosine x. If you differentiate a cosine of y, you will get negative sine of y, and remember to finish with a dy by dx when you do that. When you differentiate a 9x, you just get a 9. But when you differentiate negative 4y, you get negative 4, and remember to finish with a dy by dx. So it's like a little mantra, kind of say it to yourself. When I differentiate a y, remember to finish with a dy by dx. Now this one has got the same problem as before. Do you see there's 2 locations with a dy by dx in it, right? There's one here, there's one here. Anybody want to tell me what to add or subtract to both sides to make this closer to being the answer?
Add 4 dy by dx and then subtract cosine x.
You nailed it. So Add that guy to both sides. Take that guy here away from both sides. Is there a little deja vu happening in this question? I think I've seen something like this before, kind of feeling, right? So what's going to happen?
You can factor out a dy by dx and then divide.
Yeah.
Yeah.
Yeah, you're right. The brave amongst you will do that in one go. I'm not brave enough to try that. I should have a quick look. Pretty obvious I can't do anything else. I'm finished. I hope the more of these we do, the more comfortable you get doing them, right? In other words, you don't get freaked out, and when you see this is the next one, you're just going to follow the process, right? And if you stick to the math, it comes out each time. So here we're going to have e to the x cosine of y equals x plus y squared. Okay. Would you agree that we need to do a product rule on this side? Right, e to the x cosine y. You agree that's a product rule. So I'm going to call this guy f. I'm going to call this guy g. We're going to do a product rule on the left-hand side. On this side, things are pretty much straightforward. You differentiate x, you get 1, and you differentiate y squared, you get 2y, and remember to finish the dy divided x. Okay. Differentiate that guy, you get e to the x, leave the other one alone. Differentiate e to the, leave e to the x alone, and differentiate cosine of y. Well, that'll get you negative sine y times dy by dx. You probably don't need this line, but I'm going to put it in anyway. It just looks weird to have a negative in the middle of an expression. Obviously, if you're doing something in pencil, can't you just rub it out and put it at the start, and you don't need that line, right? Are we comfortable with where we are right now and where this came from, right? I differentiated this using a product rule, and then I just differentiated these two terms separately. And yep, this is very common. You notice that we've got two places again with dy by dx. So I am going to subtract 2y dy by dx from both sides. And I'm going to subtract that guy from both sides. And I'm going to pull out, yet again, I think this is the third time this has happened, a dy by dx from both sides. Then divide both sides by that ugly thing. That is a very ugly looking answer, but it is the answer. There are, however, and I wouldn't really call this a style point because you don't need to do it, but would you agree there's an awful lot of negatives in this answer? Right, there's a negative this, there's a negative that, there's a 1, take away this guy, a lot of negatives. You could make this slightly prettier in some people's minds by just multiplying the top and bottom by -1. Essentially, just switch everybody's sign. What would that do? Well, anything that's positive becomes negative, and anything that's negative becomes positive. And instead of writing -1 plus this guy, I wrote this guy -1. And that is also correct. And the reason I'm putting in this one for this particular question is WebDesign might not recognize this answer, but it will recognize that one. So just in case, you put this in and WebDesign says, nope, don't know what you're talking about, you may want to change it. So the rule for changing is quite simple. Essentially what I'm doing is multiplying the top and bottom by -1, but the easy way to think about it is change everybody's sign, right? Anything that's plus, make it negative. Anything that's negative, make it plus. And mathematically, that will be equivalent. And it might even look pretty. Any questions so far? I'm still processing this, right? Getting used to doing it. I mean, I can understand that. Okay, so this is something a little different going on. It's not just that it's trig that makes us a little different. It's this thing over here, which I'm going to keep for a minute. If you differentiate sine x, you just get cosine x. You always got that. If you differentiate sine y, what do you get?
Cosine y times dy dx.
Okay. We've done enough of them, hopefully, to be comfortable with it. Now, you might think, why is this going to be a problem? Well, technically speaking, this is a chain rule. This here is my inside function. So when I differentiate a cosine, I get a negative sign. And then you should finish with the derivative of what's inside, right? The derivative of the inside function. And this is where it gets a little weird. Normally, the derivative would be 1 and you wouldn't even bother doing it, right? If it said 2x, you'd do times 2. But this says x add y. Now, when you differentiate x add y, it doesn't it's not insignificant. Something happens. You get a 1 plus a dy by dx. Does that make sense? If you differentiate x add y, you get 1 plus dy by dx. So the derivative of this is actually negative the sine x plus y times the derivative of x plus y. That's the first time that that's happened. And nothing too much is happening on the right. But I have a negative sign of 1 plus something. What I'm going to have to do here is I'm going to have to distribute this. And the reason I want to do that is because I want to be able to eventually get the dy by dx's together. And right now that's not suitable. That's not in a way that's going to allow that to happen. So negative that times 1 gets you negative the sine of x add y. And negative that times that gets you negative the sine of x plus y dy by dx. So I have multiplied this by these two terms. Now we're at a place where we should be much more comfortable. Don't we have the kind of bits and pieces that we typically get? So I'm going to, as long as I do it to both sides, I'm going to get these together, right? So how about subtracting a cosine y dy by dx on both sides? and then add a sine of x plus y to both sides. Are we comfortable with what I did there, right? I essentially subtracted this from both sides and added this term to both sides, right? Can you see where we're going next then? This is where we are. What will we do on the left-hand side?
Factor out a dy by dx.
Have you noticed that the last couple of lines tend to look very much like each other? Don't you end up taking out a dy by dx as a common factor, which is what we're just doing right now. And then the last line is also pretty much happening. To find dy by dx then, don't you just divide by the ugly guy? So in this case, cosine x, add that guy, and on the bottom, that guy. I like the way that this one looks, but if web assign doesn't like the way this looks, I can give you an equivalent. Remember my little trick about changing the sign of everybody, right? All the pluses become minuses. So you could have a negative cosine x, a negative sine x add y, over a sine x add y, add cosine of y. Cosmetically, right, style points. Do either of those look better in your brain? Do you look at them and say, I think the bottom one looks a little bit prettier than the top? I guess that is really a judgment call. But in an exam, I'm quite happy with that version. And if you do this one, I'm equally happy. Can't really see many faces. That's not a good sign. So let me pause for a minute. Anybody want to share any kind of, I don't like the looks of this, or I'm okay, I think I can handle it? Okay, that's a bit better. Try and get feedback there. Let's move on to our next one. Every time you get comfortable, it's almost like I'm deliberately doing it. I'm trying to make you uncomfortable again by giving you a harder version with something else going on that didn't happen before. Here is a much more difficult version. Every time we do this, they're getting worse, right? They're getting more complicated. They got little hiccups. It's still the same process. We just have to deal with it, right? So I've got y times e to the power of sine x is equal to x times cosine of y. I don't need the details, but what method will I use to differentiate y times e to the sine x?
Combination of product and chain rules.
Yes. So we'll make that f, we'll make that j. So product rule, f dash j plus f of g dashed. And just like you said, there's going to be a little chain rule going on. We'll see that when it happens. Right. If you differentiate f, you get 1 times dy by dx, because that's what you get when you differentiate this. So I'll leave that guy alone, plus leave the first one alone. And now we're going to differentiate e to the sine x. That's where the chain rule comes in, right, Carter? E to the sine x. So what do you get there? You want to tell me the derivative of it? Carter, would you want to have a shot at it? E to the sine x. He may be speaking, I just can't hear him.
Oops, mute. Would it be sine x times e sine x minus 1? Yeah. 'Cause
Okay.
it's reduced by 1.
It's
Or
e
is
to the sine x, that bit we've got. And then don't you finish with the derivative of sine x. And that means
yeah, cosine x.
cosine x. That's it. Right, on this side, we also have a product draw. A lot easier than the one on the left-hand side was. See what we get. You get 1, leave that alone, plus leave that alone. And if you differentiate a cosine, you'll get negative a sine, finishing again with the usual dy by dx. And all I'm doing in this line here is making things look a little prettier. Really not doing anything special there. Okay, it's we finished differentiation. Now we're going to try and solve for dy by dx. And every other time this happens, we did the same thing.
I
Right.
had a question.
Yes.
Is so in the does it say x minus sine y by dx?
Over here,
Or is it x? Oh no, the line above.
here, it says x, technically it's x times negative sine y dy by dx.
Negative times.
Yeah, I don't know, it's a bit hard to do it. Negatives don't look right in the middle. Agree, they look like you're subtracting things. And in the context here, it was an x times a negative sine y. Hopefully that makes it a bit clearer. Right, do you see we've got the as long as you do it to both sides thing kicking in here? Very, I mean, uglier, but essentially the same. And so I'm going to keep this guy because I like where it is. Don't like you, so I'm going to subtract this fella here from both sides. Kind of like him where he is. Don't like that there, want it over here. So that means I'm going to subtract y e to the sine x cosine x from both sides. And I'm going to add x sine y dy by dx. So if you add x sine y dy by dx to both sides, you get that guy. And if you take this fella away from both sides, you get that guy. If you ever get to this step here, right, when it looks like this, I can guarantee the next two steps every single time, because they're going to be the same two algebra steps, aren't they? What's the first thing I'm going to do now that I've got to here?
Factor out a dy by dx.
And then what am I going to do after that?
Divide by the ugly guy.
I like your thinking. Divide by the ugly guy. You know that's not mathematical, but it does it help, you know, what you're saying, which is exactly what I would have said. The amount of style points that happen in these questions is quite minimal. In fact, I think we've only had one question where there was anything that we could do to pretty it up, you know, like divide top and bottom by 2 or something. So I guess if that's something, at least you don't need to worry, you know, about style points, right? It isn't something that happens too significantly. Are we good with that one? I hope by the time we've done 7, that you're beginning to get a feel for how you can differentiate implicit expressions. It's really 2 steps. Differentiate everything, right, with respect to x. But remember, if the bit that you're doing has a y in it, you finish with dy by dx. And then the second step is solve for dy by dx using, as long as you do it to both sides, it's okay rule. And that's question 7. Actually, it's question 8, but never mind. Let's do 7 now. This guy is a product rule. Two things multiplied together, 9x, e to the y. So I'm going to do a product rule for those two. It was there. These two guys are also product rule. And differentiating 8 is the only easy thing in the whole thing. So differentiate 9x, you get 9, leave the second guy alone. Leave the first guy alone and differentiate g, gets you e to the y times dy by dx. Differentiate this fella, you get 1 dy by dx. Leave the second guy alone. Plus leave the first guy alone and differentiate e to the x, and the whole thing is equal to 0. And I like these two guys and I don't like those two. So I'm going to subtract 9e to the y and y to the x from both sides. And that will leave me with these two terms. Pretty much finished when you reach this line, because you're going to pull out a dy by dx as a common factor. And then to finish, divide by the ugly guy. And yep, there's nothing style points I can do there. As long as you get tons of practice at these, it does get easier, right? You just get that used to doing the process that it really doesn't matter what they throw at you, because you just say it's a process. It's a product rule. It's remember to put dy by dx. Once that's finished, get all the dy by dx's together, pull it out as a common factor, divide by ugly guy. Well, for the last one for today, question 9. This one is an example of just because you can doesn't mean you should rule. You might be thinking, oh, God in Himmel, I am going to have to differentiate a quotient rule. And I don't like quotient rules at the best of times, but I definitely don't like quotient rules with y's in them, because I'm not even sure how that's going to work, right? That would be my natural reaction. I don't want to do this. So let's not. Let's rewrite this in a form that's going to be easier to differentiate. And I'm going to do that as a clue. What do you think I'm going to do to this expression?
Multiply y squared plus 1 by x squared plus y.
We call that, at least some of you would call that, me included, when you call that cross multiply. That makes sense? Some of you may have different name for it. Now, I'm not going to leave that, mostly because I could do that as a product rule, but it would be very ugly and messy, and I'd probably make a mistake. So I'm just going to FOIL this out. So it's going to be x squared y squared plus an x squared plus a y cubed plus a y equals to x squared. So far, so good. Right. Now, this doesn't happen very often, but when it does, it's kind of nice. Can you see any way of simplifying this expression?
Do the x squares cancel out?
They do indeed. Now, if you didn't notice that, it actually wouldn't matter because it would sort itself out, later on. If you like that, if you see it, it's great. If you don't, it's no big deal. So haven't we really just got, and for want of a better word, a typical implicit expression question there, right? So I'm going to differentiate that instead of differentiating yikes, right? So this is a product rule. If you differentiate y cubed, you get 3y squared. Remember to finish with the dy by dx. If you differentiate y, you get 1. Remember to finish with dy by dx. And if you differentiate 0, guess what? You still get 0. Differentiate the first guy, you get 2x. Leave the second one alone. Leave the first one alone and differentiate y squared, and you get 2y dy by dx. And then just writing down all the other terms. But instead of writing one of these, just write dy by dx. Okay, differentiation has finished. What's going to happen next? There are 4 terms here.
You can factor out a dy by dx.
You will eventually, but do you want to do it quite yet? Because this term doesn't have a dy by dx in it, does it?
Oh, you have to subtract the 2xy squared.
Okay. And now we can factor out, just like you said, dy by dx. So I get that guy, I get that guy, I get that guy. Right. In fact, isn't this the typical last 2 lines, right? Factor out the dy by dx and then divide by the ugly guy. So if you can ever get to that line there, you're home and dry. Because you're going to finish with the same 2 lines of algebra that you always finish with, which is factor out a dy by dx and then divide by the ugly guy. And yeah, there's no style points. I can't do anything to that. How do you feel about implicit at the end? You feel you got a good grip of it, right?